Okay, lesson 25, we're going to go through the workbook questions since there's not a checkpoint. So we're going to start straight off with question 1 since it is a proof. Use the information diagram and proof to fill in the blanks. Given triangle ABC, prove that the ratio of sine A divided by A is equal to the ratio of sine B divided by B. We're given our diagram right here of triangle ABC with its labels. So segment CD is drawn perpendicular to segment AB. Therefore, H is the height of triangle ABC. In triangle CDA, blank equals H over B, and in triangle CDB, blank equals the ratio of H over A by the definition of blank. Okay, so what ratios are they looking at? So in triangle CDA, we have a ratio of H to B. Now, using our reference angle of A, I could have H is the opposite side of angle A, and B would be the hypotenuse in this triangle. So I'm thinking, what trig function is the ratio of the opposite side length to the hypotenuse side length? And that would be the sine. So sine of A is equal to opposite, which is H, over our hypotenuse, which is B, both by substitution. Or if I changed my reference angle, if I changed my reference angle and I wasn't looking at from angle A's perspective, but I was looking at angle C's perspective, H would be the adjacent side then, and B would be the hypotenuse, and our opposite side of angle C would be right here. And since the ratio right here was H over B, the trig function that has the ratio of the adjacent side length to the hypotenuse side length would be cosine. So I could have cosine of C is equal to H over B. So there's two options for writing the ratio of H over B in our triangle CDA. Now I'm thinking back to how am I going to decide between which one is used, and thinking back to the proof, we need to prove that sine of A over A is equal to sine of B over B. So since I need to prove sine of A over A's ratio, I need to include it somewhere in the proof. So I'm going to choose sine of A is equal to H over B. So X is going to be sine of A. And then the next triangle we need to look at is triangle CDB. So triangle CDB. And I'm going to use what we need to prove as a little bit of guidance. So sine of B, so I know B needs to be our reference angle. So labeling this according to angle B's perspective, H is going to be our opposite side length, A is the hypotenuse, and this length DB is our adjacent. So then, since the ratio is H over A, I'm thinking, what trig function gives me the ratio of the opposite side length, since that is H, over the hypotenuse side length, since that is A, and that is our sine. So sine B is going to equal opposite side length over our hypotenuse side length. This is going to equal that ratio. So we have sine of B. And then by the definition of blank, by the definition of our sine function, sine is our ratio of our opposite side length to our hypotenuse side length. And then it goes and explains the rest of it. So question 2, consider the following triangle. If measured angle B is equal to 17 degrees, measured angle C is equal to 140. Side length AC is equal to B and side length AB is equal to 15 units. What is B approximately? So I'm thinking to myself, is this going to be the law of sines or is it going to be the law of cosines? And how I can tell the difference between them is law of sines. I will be given two angles and one side, or two sides and one angle. And since we have two angles and one side that is given, and I'm looking for the other side length, I can set up that ratio. So I'm going to set up the side length. B is to the sine of its angle. So B's side length is to the sine of its opposite angle, which is 17 degrees, as 15 is to the sine of its opposite angle, which is sine of 140 degrees. Now 15 divided by sine of 140 is a number. Since we have B and we're trying to solve for it and it's being divided by sine of 17, I'm going to use the multiplication property of equality and multiply by sine of 17 to both sides. So sine of 17 times 6 is sine of 17 degrees times 6 divided by sine of 17. Oh, that's not 6. That's a B. Sorry. I'm going to use, well, I can't use big B. That's an angle. So little b. So sine of 17 degrees times b is sine of 17 degrees times b divided by sine of 17 degrees, which is going to equal 15 divided by sine of 140 times sine of 17. We multiply our numerators, so 15 times sine of 17 divided by sine of 140. Now sine of 17 divided by sine of 17 can be reduced down to a form of 1 since it's the same number being divided by itself. So then we have 1b is equal to 15 sine of 17 times sine of 140. We're going to use our calculator to find our decimal approximation times sine of 17 degrees, close that parentheses. We're going to divide it by, hold on. Since there is more than one number in our numerator, we need to include parentheses. So parentheses 15 sine of 17, and please make sure you are in degrees. Close parentheses, close parentheses. That is our whole numerator. So I want that as one whole group, and parentheses indicates your groups. So that's one whole group times sine of 140. Divided by sine of 140, which is equal to 6.822. So these approximately, we need to round it to the nearest tenth. So I'm going to ask myself, is 82 closer to 80 or closer to 90? And that is closer to 80. So we're going to have approximately 6.80, which is 6.8. So then we have 6.8 right there. Units. Question 3 is similarly set up. Question 2. Question 4 are proof. Use the information diagram and proof to fill in the blanks. Given triangle ABC, prove that a squared is equal to b squared plus c squared minus 2bc cosine of angle A. So in triangle ABC, a segment CD is drawn perpendicular to segment AB, therefore H is the height of triangle ABC. We want to show that a squared is equal to b squared plus c squared minus 2bc cosine of A. By definition, sine of A is equal to the ratio of H over B. So angle A was our viewpoint. We had the opposite side over the hypotenuse. Therefore, using the multiplication property of equality, we have H is equal to B sine of A. So they multiplied B to both sides in order to solve for H. Also, by definition, cosine of A is equal to S divided by B. Therefore, using the multiplication property of equality, we have S is equal to B cosine of A. Using the segment addition postulate, we can state that C, the side length of A to B, is equal to S plus T. And that T is going to equal C minus S, follows from the subtraction property of equality. So they took this positive S and subtracted it to both sides in order to create this statement T. Using the Pythagorean theorem in triangle CBD, we have that a squared, that's our hypotenuse, is going to equal h squared plus t squared. So by substituting for c, we have a squared is equal to h squared plus c minus s squared. This should say by substituting for t, we have c minus s, because t equals c minus s squared, and there is our t. Now we substitute for h and s. So h had been found to be b sine of A, and s had been found to be b cosine of A. So there is our blanks for 1. 1 is going to be b sine of A, since that was what h was equal to. And s was equal to b cosine of A. So there are our blanks. Okay, we're going to jump to using our law of cosines. So use triangle ABC and the law of cosines to answer the following question. Given measured angle B is equal to 56 degrees, segment AB is equal to 8 units, and segment BC is equal to 10 units, what is the approximate value of B? So how I remember the law of cosines is in relationship to the side lengths. So the side I want to find is little b. Is right here. Do I have its opposite angle? Yes. Do I have the adjacent side lengths to that angle? Yes, I have 8 and 10. Then I can use the law of cosines. So law of cosines, I need to know the angle opposite the side I'm finding, and I need to know the side lengths that are adjacent to that angle. So then I remember the side length that I'm wanting squared is going to equal the adjacent side length squared plus the other adjacent side length squared minus 2 times our adjacent side lengths times cosine of my angle opposite the side length I wanted, which is 56 degrees. So I just remember it based on the relationships in our triangle to each other. So now, since we have no missing variables on our right hand side, I'm going to type that straight into our calculator. So I'm going to type in, and since we're subtracting this whole group, I'm going to put it in parentheses because parentheses indicate groups. So I have 8 squared plus 10 squared minus parentheses 2 times 8 times 10 times the cosine of 56 degrees. Make sure that it is in degrees. Then we hit equals. That's going to equal, b squared is going to equal 74.529, ... Now that's the value of b squared. I want to find the value of b. So I think, okay, the inverse operation of a square is to square root. So then the square root of b squared is b. And that's going to equal the square root of 74.529. So I hit the square root of 74.529,135, ... And I'm not going to, okay. For rounding sake, that's as far as I'm going to go. So we have 8.6330 for our side length of b. Now they want our answer entered rounded to the nearest tenth. Okay, so then nearest tenth, I'm just going to group the tenths and the hundredths. I'm going to ask myself, is the 63rd closer to 60 or closer to 70? And that's closer to 60. So b is going to equal 8.60, which is just 8.6, rounded to the 10th. Okay, so now this one is going to ask you which law would be best to use to solve for y. Now this is where you evaluate what is given and what you need to find. So I'm going to start with the law of cosines. In the law of cosines, I know that for the side length that I want to find, which is y, I need the opposite angle, which is 20 degrees, and I need the two adjacent sides to 20 degrees. So I have the 20 right here for one adjacent side, but I'm missing this adjacent side length's value. So I can't use the law of cosines there because I'm missing one of the adjacent sides to my angle of reference. So law of sines, I know that I need a side length and the opposite side and the opposite angle. So I have a side length here that I want to find and its opposite angle. Check. Now do I have another set of that to set up my ratio or my proportion? So I have another side length and the opposite angle given. So yes, I could use the law of sines. Alright, and your quote for your help is going to be by Charles H. Spurgeon. Giving is true having.